the wave advantage system 1.1, which is characterized by a Pegasus topology, and with the default annealing time and schedule. So regarding the number partitioning problem, well, it's an NP-hard problem, and the task is quite simple. It consists in splitting a set of numbers into two subsets, such that the difference between the sum of the elements in the first subset and the sum of the elements in the second subset is minimum. There are some classical heuristic and exact algorithms that can be used to solve it. For instance, we could use a greedy algorithm, which consists just in sorting the elements from the largest to the smaller, and then assigning each element to the subset whose sum is currently lower. Otherwise, there is the karma-karp heuristic, which is the basis of the complete karma-karp algorithm we used for comparison. So I will just describe the last one. The complete karma-karp is an exact and, in the worst case, exponential time algorithm, which is based on a depth-first search of a binary tree, whose left branch consists in replacing the two largest number with their difference. So the two numbers are, in practice, are placed in different subsets, whereas the right branch consists in replacing the two largest numbers by their sum. Hence, the two numbers are placed in the same subset. And the algorithm stops when a perfect partition is found. Then a linear procedure is required to obtain the solution, since the algorithm does not provide it directly. And in this work, we have used the implementation provided by Pedroso and QUBO as a comparison. Regarding the QUBO formulation, well, we took the formulation from the work by Glover, Kochenberger, and Du. So given a set of numbers S, S1, Sn, with C being the sum of all the values, the QUBO formulation requires n binary variables xi, and xi is equal to 1 if the corresponding value si is placed in the first subset, 0 otherwise. The QUBO matrix Q is built as shown in the bottom. Basically, first of all, we need to consider the squared difference between the two sums, and then to drop the constant c squared and the multiplicative factor 4. At this point, we have the problem in the canonical QUBO formulation, and the entries of the QUBO matrix Q are filled like shown on the right. Regarding the experimental setup, we run all the experiments on the cloud interface provided by the wave, this LEAP, and the methods taken into account are QALS in the C++ implementation, the hybrid solver provided by the wave, which runs in parallel multiple methods, which could be either classical, like a taboo search, or pipelines composed of decomposers, solvers, and the composers. The decomposers split the problems into multiple sub-problems, which are solved by the solvers, which can be either, again, classical or quantum, and then the final solution is reconstructed by the composer. And finally, there is the complete karma-karp algorithm that I just described. Regarding the parameters used for QALS, they are reported in the table in the bottom. While the first two parameters are related to the probability of perturbing the permutation matrix, the permutation vector. And the value Q instead is related to the probability of perturbing the solution retrieved from the annealer. N is the number of iterations at constant probability. Lambda 0 is the initial scaling factor for the taboo matrix S. And the important parameter is actually K, which is the number of reads, which has been set to 10, which is a quite low value. And finally, there are the two parameters related to the convergence. And here are shown the results obtained, and the first column dimension shows the number of values taken into account for a problem instance. The range instead represents the upper limit on the numbers generation. And basically, it's the maximum value we can find in the set of values S. The set's difference is the difference between the two resulting sets. And then we have the time expressed in seconds and the number of iterations for QALS. So QALS actually did not perform as well as expected. Indeed, the hybrid outperformed QALS both in terms of quality of the solution found and execution time. However, as I just said, hybrid exploits multiple solvers in parallel, and they can be also classical methods. And basically, there is no way to know if the solution has been provided by a classical or a quantum method. But in general, hybrid performed really well. It has been able to find a really good solution, not always the optimal. But the method that has outperformed all the others is the classical one. Indeed, it has been able to find the perfect partition in all cases. And as you can see, also for these problems with higher dimension, and also in a really low time. And this basically means that the problem, although the problem is NP hard, it is not the problem we can for which we can expect an advantage by using the quantum methods, especially if a perfect partition exists. And another important thing to mention is that the number of reads for QALS is really low, 10, and we can expect an improvement in performance by increasing this value, but the time at our disposal was not enough to increase this parameter. Instead, as concerns TSP, well, it's another NP hard problem. The task consists in finding the shortest route through n cities, given the list of cities and the pairwise distances. Not all the cities are necessarily directly connected. And the route must visit each city exactly once and must return to the origin city. And this problem can be also seen as the problem of finding, for a graph, the Hamiltonian cycle such that the sum of the weights of the edges in the cycle is minimum. And this alternative view of the problem provides also a QUBO formulation that we took from the work by Lucas. And so given n nodes or n towns, the QUBO formulation requires squared n binary variables xij, and xij is 1 if the node I is placed in the position j in the cycle, 0 otherwise. In the bottom of the slide, we can see the problem, the Hamiltonian describing the problem. And as opposed to MPP, which has a natural representation as QUBO, here we have to also to embed some constraints. Indeed, TSP is a constrained problem. And the Hamiltonian HA is the one encoding such constraints. So the first term represents basically the constraint according to which a node must appear exactly once in the cycle. The second term instead represents the constraint according to which there must be only one node in each position. The last one instead basically represents the validity of the cycle. Two towns could not be directly connected, and hence a cycle could be invalid, for instance. Instead, the Hamiltonian HP is the one encoding, let's say, the objective function, since the values W, U, V are the weights of the edges. So the minimization of it's the minimization of the cycle total weight. The coefficients of these penalties, A and B, are positive constants. And there is also an additional condition that makes not favorable to violate the constraints. And in particular, the coefficient A must be larger than B times the maximum edge weight. In the experiments, we set B equal to 1 and A equal to n times the maximum edge weight. The last step to obtain the QUBO matrix Q is the renumbering of the variables xij, which has been performed in the way shown here. And at this point, we can obtain easily the QUBO matrix from the Hamiltonian. Indeed, the value in the cell Qij will be just the coefficient of the term xi times xj in the Hamiltonian H. Regarding the experimental setup, well, we ran again the experiments on the LEAP, and in this case, we consider the 4 methods. First of all, a classical brute force method implemented in C++. Then, again, the hybrid solver provided by the wave. The third one, embedding composite, is exactly the direct embedding of the QUBO matrix inside the annealer using the tool provided by the wave, but with the solution refinement, which is a procedure I will describe in a while. And finally, there is QALS in the Python implementation, in this case, again with the solution refinement. Basically, the solutions found by both embedding composite and QALS were not valid. Actually, embedding composite has no guarantees to find a solution that satisfies the constraints. Instead, regarding QALS, the main issue is probably the fact that the problem, only part of the problem is embedded, is mapped to the annealer topology. And the problem in this case includes also the constraint. So the constraints are not fully represented inside the machine. And so a refinement procedure was needed in order to evaluate the quality of the solution. And the refinement procedure we used is a really simple procedure. It is the one presented here. The first step consists in identifying the nodes that represent the solution for a cycle position. And these nodes are marked as unavailable. Then, for each cycle position in which there are multiple possible nodes, one of them is randomly assigned to that position, of course, only considering the available ones, and that node will also be marked as unavailable. The third step is the random assignment of a node to one position if it is assigned to multiple ones, and the other positions are reset. And finally, there is the random assignment of the remaining nodes to the remaining positions. If the original solution is valid, no change is made by this refinement procedure. And regarding the parameters, while the edge weights in the problems taken into account are all real numbers in the range 0-10. And the number of reads for embedding composite has been set to 5, as also for QALS. We can see in the bottom that the parameters are quite similar to the ones used for MPP, but the main difference is a lower number of reads, K. And here we can see the results. And in this table, TSP size represents the number of towns or nodes in the graph. The QUBO size is the number of binary variables. Mu is the average TSP cost with respect to the number of runs performed. And the TSP cost is defined as the sum of the weights of the edges in the cycle. Sigma is the standard deviation, the corresponding standard deviation, and the time, again, is expressed in seconds. So let us first consider the TSP size equal to 10. In this case, we can see that that QALS has performed better than embedding composite, but worse than hybrid, which has found a really good solution compared to the optimal one found, of course, by the brute force method. Instead, regarding the sizes 12 and 14, we have that embedding composite has performed better than QALS, but again, not as good as hybrid, which has found still good solutions, but not as good as the one found for the problem with size 10. However, 14 is also the maximum size that can be addressed using embedding composite. Indeed, starting from size 32, only hybrid and QALS work. Also, the brute force method becomes unfeasible in terms of execution time. Also, here we can see that the increase of the execution time when increasing the size is exponential, of course, since it is an NP hard problem. And actually, for all the problems with size between 32 and 72, we have that hybrid has turned out to be better than embedding composite, both in terms of execution time and the quality of the results obtained. And finally, we have the size 74, in which only hybrid works. And this could be due to either the usage of just classical methods or to the pruning of some qubits due to the sparseness of the QUBO matrix. In general, we can say that QALS has fulfilled its empirical goal of addressing problems that are not directly mappable to the annealer topology. Indeed, the maximum size that can be addressed with embedding composite is 14. And unfortunately, all the solutions found by QALS were not valid, as also for embedding composite. And actually, the performance of these two methods could be improved by increasing the number of reads, which is really low. But again, the time at our disposal was not enough to increase this parameter. And again, we have to highlight that hybrid reaches good results, but it exploits also classical techniques. So here, so let's move to the conclusion. Here there is a brief summary of the main points. So in this work, we have presented two implementations of QALS with some improvements with respect to the original formulation. And the implementation in QALS in C++ has the advantage of the efficiency in the classical part of the algorithm, the scheme, whereas the implementation in Python, the advantage of the other implementation is a native interface with the annealer provided by the Wave, whose APIs are in Python. We have empirically evaluated this approach on two different problems. First problem, NPP, which is naturally representable as QUBO, and a second problem, TSP, in which instead it requires setting some penalties to encode the constraints of the problem. Regarding MPP, well, the classical exact algorithm has outperformed all the other methods tested. And hence, again, it's not probably the best choice for testing quantum techniques, since there are some classical algorithms that can solve it quite well. And hybrid also outperformed QALS, but exploiting also classical techniques. Regarding TSP, instead, with TSP, we were able to prove that QALS is able to process problems that are not directly embeddable in the annealer topology. But again, hybrid achieved better performance than embedding composite and QALS, whose solutions were always invalid. So in conclusion, we could think that QALS has some practical applications in hard problems that cannot be directly represented in the annealer topology, but also the number of reads this parameter should be increased in order to achieve better performance. Whereas hybrid is a necessary baseline, but again, it exploits multiple methods in parallel, so it cannot be used to draw scientific conclusions. And that's all. Thanks for your attention.
Thank you very much, Enrico. Thank you. First of all, let me apologize for forgetting to start the recording until after your introductory material. Many apologies from me for that. But secondly, let's offer this up for questions. So does anybody in the audience have questions for Enrico? Dennis, go ahead.
Yeah, hi, Enrico. Does my mic work?
Hi.
Can you hear me?
We can hear.
Yeah.
Okay, very good. Yeah, thank you very much. So it's indeed impressive that the 72 TSP was embeddable using QALS. Can you give me a bit more intuition about how QALS actually works? Like what does it do to find the embedding?
Yeah, well, basically, in order to embed the problem inside the machine, we use the taboo matrix, which is initialized at the beginning to a zero matrix. Then, throughout the iterations, the matrix is filled with the rejected solutions, which are then summed and rescaled first, and then summed to the QUBO matrix. In this way, we are able to let's say, solve not only sub-problems, but also the entire problem, since there is some additional knowledge about the solutions that have been rejected inside the taboo matrix. And then actually the embedding part is just like an Hadamard product. So we are using only the nodes and the edges provided by the topology, performing a direct mapping from the matrix to the adjacency matrix of the annealer.
Okay, thank you very much. And maybe one follow-up questions. One question about the how did you generate the TSPs? I mean, in principle, you know the exact solution, right?
Yeah, actually, we generated them randomly. So we had to run also the a brute force method to know then the solution.
Okay, I see. So with randomly, you mean like you just sample some distances, like from a Gaussian distribution or something like that between the
Exactly.
cities. Okay, thank you very much.
You're welcome.
Maybe I could ask a question. So you effectively end up with some kind of embedding of your problem onto the D-Wave hardware using this iterative approach. And I'm wondering whether the embedding you get looks a bit like the sort of minor embedding that would be generated using minor, for example, or is it completely different? Is it qualitatively the sort of embedding that somebody like me would guess?
It's actually different, I would say, because the minor, when embeds the problem, typically creates chains of qubits.
Yeah.
So the qubits are chained in order to represent logical qubits and have higher connectivity. Instead, in this approach, we are just using the edges and nodes that are available without creating chains. And so we are just using the connections that are available in the machines. And the embedding part is mainly related of the entire problem is mainly related to the permutations and the usage of the taboo matrix.
But you're telling me that experimentally you don't just get chains, you get something that's different.
Yeah, we are just basically providing the annealer with the weights of the connections that are available in the physical topology of the annealer.
Okay, fine, thank you. Kathy, you have a question.
I do. Yeah, hi. It was an interesting talk, and I guess I just want to check my understanding of some of the details. When you say the hybrid solver, are you talking about the open source hybrid sandbox that is available for anyone, or the hybrid solver service, which is the service that is available by subscription?
No, actually, it's the, I would say it's we used the one probably is the one available by subscription. It's the hybrid solver provided just by the D-Wave Ocean library, but at the moment I really don't know if it is available without subscription. I would say no, probably because it's it also consumes annealing time, and so you need somehow.
Like, was it the CQM solver specifically? I was wondering. Did you run the code yourself, or did you sort of submit it, and was somebody paying for the results?
No, we have just access to the machine through the Unix Supercomputing Center, and without, I would say, additional payment. No.
Yeah.
So.
Okay. Yeah. So that probably was the. Well, I guess I don't know. I won't say probably because I don't know.
I think it was the service.
Yeah, I was wondering if someone from Ulick might know that. Thank you, Dennis. Okay, thank you. Second question is, if you go back to your TSP, that grid of all the information about the problems. Yeah, I just need an example. That was fine.
The solution, yeah. Or yeah.
Yeah, this is fine. So if I understand you correctly, the TSP, we see this TSP sizes and the QUBO sizes. And do I understand that the brute force solver solved the TSP in its original formulation, whereas hybrid and these other ones solved the translated QUBOs that were larger? Is that correct?
Yeah, actually, the experiments were run by my colleagues. So let's say the brute force solver was implemented by them. If I remember correctly, the solver actually solves the original TSP problem.
Okay, and I would think too with the number partitioning that if you're using Karmakar-Karp's algorithm, that's a number partitioning algorithm. So
yeah,
that would be the same as well. Okay, so I guess if you're pursuing this for future work, I'd be interested to know how much is that difference in solving the big problem versus the translated problem that is creating the performance difference here. And it might be interesting to take a purely classical solver that solves QUBOs as sort of, you know, a comparator for QUBO, the QUBO part of the equation. That might be an interesting.
Yeah, that would be interesting. Yeah.
And I guess my other question was the same as Dennis's about, so generating the TSP problems, it wasn't like a geometric Euclidean distances. It was actually random distances among in nodes.
Yeah.
And what about the partition?
Yeah, the number partition actually the same. Yeah, where sets of randomly generated number. So
Okay, so there's a possibility that unstructured random instances are unusually easy for heuristics because they're degenerate. They have a lot of optimal solutions, and it's kind of easy for a greedy solver to just find something. So it might be also interesting to check that these aren't easily solved by greedy in the original formulation. You know, if you can just roll downhill and find the solution, they're
yeah. Also, a posteriori, I thought that it would be interesting to try to solve some let's say sets of numbers that do not have a perfect partition. In this way, the solver wouldn't be able to stop
early. Yeah, for example, that might be an interesting thing to look at as well. So, all right, thank you.
Thank you, Kathy. I see there is a question in the chat. So Ying is asking, what is the difference between quantum annealing and quantum adiabatic evolution? Do you want to answer that one, Enrico, or shall I answer that one?
If you want, actually, you can answer that. Yeah.
So I guess quantum adiabatic evolution is a theoretical construct where you're in a closed system, you're guaranteed to stay in the ground state at all times, and then you evolve sufficiently slowly that you stay in the ground state at all times, so that if you initialize in the ground state, you end in the ground state. That is not what is happening on the D-Wave machine. So D-Wave does quantum annealing, where as well as initializing in the ground state, there are unquestionably transitions to excited states due to various noise sources, including thermal noise. You may also get transitions to excited states because you're undoing a Landau-Zener transition through a minimum gap. And so you have a rather more complicated process where you're sort of near the ground state, but you're exciting in certain places. You may also relax so that you end up in the ground state at the end. So my brief summary, Ying, is that quantum adiabatic evolution is essentially a theoretical construct, whereas quantum annealing is a much more experimental, real-world approximation, if you like, to an adiabatic evolution. It's a pleasure. Good. Any further questions for Enrico? I don't think I see any more raised hands or questions in the chat. So let's thank Enrico once more for a very interesting talk with lots of nice results. That ends the seminar. I look forward to seeing you in 2 weeks' time for the next INQA seminar. Thank you, everyone.